Okay, well, welcome to today's stream. We have 5 seconds to go, so we're just gonna go straight into it. Day 11, here we go. Welcome if you're joining or joining the stream, watching the video. It's good to be here doing this today. So, day 11, Dumbo Octopus. All right, you enter a large cavern full of rare bioluminescent Dumbo octopuses. Oh, these are like the really cute octopuses, aren't they? Like, hang on. Let's just take a real quick look at this video. I know it's a bit of a, yeah, it's those small cute octopuses. Um, if you haven't seen, I think it's the Kurz gesagt octopus video. They have a really cute, oh, maybe it's not the Kurz gesagt video. Okay, never mind. I can't remember exactly who that video was from, but maybe it's a TED Ed video. There's a TED Ed video with octopus. It's really, really cute. It's got a Dumbo octopus at the end. So make sure you go check that out. So, anyway, that's a waste of a minute. They seem not to like the Christmas lights on your submarine. So you turn them off for now. There are 100 octopuses arranged neatly in a 10 by 10 grid. Each octopus slowly gains energy over time and flashes brightly for a moment when its energy is full. Although your lights are off, maybe you could navigate through the cave without disturbing the octopuses if you could predict when the flashes of light will happen. Each octopus has an energy level, your submarine can remotely measure the energy level of each octopus, which is my puzzle input. Oh, okay. So this feels like some kind of Conway's Game of Life sort of like automata sort of like automata. I can't read automata sort of like puzzle. But we'll keep going. The energy level of each octopus is a value between 0 and 9. Here, the top left octopus has an energy level of 5, great, and the bottom right has 6, and so on. You can model the energy levels and flashes of light in steps. During a single step, the following occurs. First, the energy level of each octopus increases by 1. Then, any octopus with an energy level greater than 9 flashes. This increases the energy level of all adjacent octopuses by 1, including octopuses that are diagonally adjacent. If this causes an octopus to have an energy level greater than 9, it also flashes. This process continues as long as new octopuses keep having the energy level increased beyond 9. An octopus can only flash at most once per step. Finally, any octopus that flashed during this step has its energy level set to 0, as it has used all its energy to flash. Adjacent flashes can cause an octopus to flash on a step even if it begins that step with a very low level. Consider the middle octopus with 1 in this situation. After step 1, it will have flashed because it's got 8 octopuses around it that flashed, and they all cause it to increase by 1. An octopus is highlighted when it flashed during the given step. Here is a larger example of how that progresses. So after 1 step, after 2 steps, they all flash. After 3 steps, they all flash. 4, they all flash, and so on. Cool. After 100 steps, there have been a total of 1,656 flashes. Given the starting energy levels of the Dumbo octopuses in your cavern, simulate 100 steps. How many total flashes are there after 100 steps? Okay, so for the first time, I'm going to actually use the test input as my input for this challenge, the worked example input. And the reason for this is because I'm not confident that I can write an algorithm for this and then get it to check. But in this case, this specific input has been worked through and it's got examples. I know that the answer is going to be 1656. So I'm going to write the algorithm against this data set and then see what happens afterwards. So the best way to do, the first thing I'll probably do is convert this into an array of ints. In fact, in this case, we can actually do 10, 10 like that. Although in in Go, it's quite tricky to actually use. In Go, if you give if you don't have a fixed dimension, it's called a slice. And if you have a fixed dimension, it's an array. And slices generally tend to be easier to work with than arrays. That's because arrays have really weird constraints on because they have a fixed size. So I'm actually going to keep it like this. What I'm going to do is I'm going to pre-allocate 10 size 10 in one dimension, and then pre-allocate an array of size 10 in the other, a slice of size 10 in the other dimension. And then we're going to read each string into it, I believe. There's actually a neat little trick you can do here, because if you index into a string, it's a rune, which is an ASCII. In this case, because these are all numbers, we know that these are ASCII numbers. So I can actually very likely do this instead. Grid I j equals data I j minus the number 0, the character 0. And this should give me oh, byte, my bad. Data type issues. And this should give me the actual numbers I want. So you can see in my output that I now have as an integer the numbers 5, 4, 8, 3, 1, 4, 3, 2, 2, 3, and so on. So this has been transcribed correctly. So this is just a neat little low-level sort of hack if you know what you're doing. So I probably want a function called step, just because it's easier to think about in this way. I probably want to copy the array. Do I want to copy it? I don't have to copy it. It might be easier if I don't copy it. And so, okay, it's probably better if I do copy it, immutable and all that stuff, but it's probably easier to write if I don't copy it. Just copying two-dimensional arrays are a bit annoying. What I know I will need is an array called updated, which is going to be an array of bools. Now, just to keep things more simple, this is going to be y times 10 plus x is the index into this array. I'm just going to make it one-dimensional because it's easier to initialize, like this. Or I wonder if this is an initialized array. It might be. We'll see. So first step, increment 1 across all the values in the array. So len grid like this. Len grid y, which is, I mean, these are all going to be 10 no matter what. Now I think I have a function called format fimp. Okay. Just to get that indented correctly. Grid y x plus plus. I think we'll do this in multiple passes. So the first pass, we just increment everything. You can probably do this in the same pass, but it feels easier if we just keep looping over it, because what we'll probably need to keep looping over it to check for any chain reactions anyway. So pass 1, just increment. Pass 2 is going to be if anything is over 9, it explodes. or flashes, sorry. If it is greater than or equal to 9, it flashes, right? Yeah, it flashes. So that's what this updated is. If I call it flashed, it'll probably be a bit easier to remember how this works. So flashed is going to be true. Right. So if this cell has already flashed, we ignore it. If it hasn't flashed and it is greater than or equal to 9, then it has flashed, and we need to increment all the eight cells around it by 1. So if oh, this is annoying. The 8 cells around it. I think I'll write this out. If y minus 1 is greater than or equal to 0, and grid y minus, okay, if it's greater than 0 or equal to 0, then this is the top row. If x minus 1 is greater than or equal to 0, and grid y minus 1, x minus 1, sorry, then this plus plus, grid y minus 1, x, which is always going to be valid, plus plus, x plus 1 is less than len grid y, less than 10, grid y minus 1, x plus 1, plus plus. Oh, I decided to do this, did I? Never mind. Forgot that I made a decision on that. Cool, that compiles. That's if y minus 1. And then we have the same thing, but this time for y equals 0, which is never going to be an issue. If x minus 1 is greater than or equal to 0, this. If x plus 1 is less than that, then we increment that. Then we have one more set of cases is for y plus 1, and we do the same thing. So this will have updated all 8 cells around my current cell. Yeah, and so then we just need a break condition. So updated something equals false. If this, then updated something equals true. Here we will check. Oh. Yeah, okay, so here, repeat. So we only need to repeat if we updated something, right? If updated something, we repeat. So if while updated something, we've got to reset it. So then this repeat will work. So basically, yeah, we will keep updating the grid until we don't update anything else anymore. And we keep track of the things that we've already updated using this updated or flashed bool. So at the end of this, we just need to count how many updates. So we need another set of these for loops. You know what? We don't need these for loops. We can just count. Cool. So we have this count. It might be easier if I put this count at the bottom actually, because what we're going to do here is we're going to say count and set flashed octopuses to 0. It'll just be easier to read because it's a shorter block. So for flashed, then flashed y, if flashed yx, grid yx equals 0 and count plus plus, return count. So the step function will update the grid and give us a count of things. So after the first step, count should be 0. And this is what we're going to check. Okay, got some index out of range stuff happening on line 90. Right. Wait. Oops. Less than len grid. And yeah, that should be good. We got 35 after the first round, which is wrong. There should be no updates after the first time, right? So let's see. Let's print out the grids. Let's print out the grids. I'm going to make a function for that this time. What's the best way to do this? We'll say for each row in the grid, let's we'll say for each row in the grid, let's print out oh, they're not strings, are they? Okay, we'll do it the low-level way. Cool, and we want to print out the second grid. Okay, so something's going wrong here. I wonder what it is. Nothing should reach 9 after the first round. Nothing should reach 9 after the first round. So the first time I do this, this should all just go through and none of this should happen. That is so weird. What's going on here? Like it's kind of there, but it's not quite there. Like some of the values got updated the way we expected it to, and some of them didn't. Right. Let me just do a little check here. What does that look like at that point? Oh, did it say greater than 9 or greater than or equal to 9? Greater than 9. Ah, that's what I did wrong. Greater than 9. So this is a case of me not reading the problem description correctly. And we should have 0. And then we should have 35 on the second one. 1, 2, I'm just counting this grid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. 36. Or did I just count it wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 19, 25, 31, 35. 35 is correct. Okay. So count is going to be 0. We're going to do 100 loops. Count plus equals step grid. We're going to dump the grid at the end, and we're going to print out the count, and it should be 1656, and the grid should look exactly like this, which it does, which is amazing because that means it's working the way that it's supposed to be. So we're going to swap out the test data with the actual data that we get in my input, and it says the answer is 1723, which hopefully is going to work. All right, it's great, it's working. Let's keep going. So what's happening now? Seems like the individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. In the above example, the first time all octopuses flash simultaneously is in step 195. And they all flash simultaneously. If you can calculate the exact moments when the octopuses all flash simultaneously, you should be able to navigate through the cave. What is the first step when they all flash simultaneously? Well, there's a couple of ways to do this, but the easiest way is I'm just going to set this to 1,000. And then all we're going to say is if count equals 100, then they all flash simultaneously. And then we're going to print line, simul I plus 1, I think is the correct answer, and break. So I think I plus 1 is the correct answer because of the way we're doing indexing. Not going to make that mistake again, so I'm just going to double check this first. The answer here, it should print 195, I believe. Wait a second. Oh, I'm not using, oh no, I am using the test data. What is going on? Is count not 100 when they all flash simultaneously? Oh, if count equals 100, whoops. This count equals step grid, count plus equals this count, then we go. This should show the correct number that we're looking for. 195. Okay, so the I plus 1 is correct because the answer here is 195. So now we just swap this out and run it on our own input data. Oops. And what do we get? 327 is my simultaneous one. We got it. All right. Cool. Yeah. Okay. I like that problem. This was a cool problem. Again, it's a little bit tricky to do in Go just because of the this sort of thing. It's just a mess. 2D grids are just kind of a bit of a headache to do. Again, if I did this in JavaScript, I mentioned this a few days ago. In JavaScript, whenever I do these coordinates, not the most efficient way to do it, but for these sort of challenges, I just use a map, and I use the XY coordinates like this as an index into my map. And the cool thing about this is that if it doesn't exist in the array, you just get an undefined back. Right? If it doesn't exist, if x becomes -1, for example, I just get an undefined. And that's much easier to check than having to pre-check whether I'm outside the bounds of the array or the slice, and then going, okay, if I'm outside of the bounds, then don't do this check. But if you are inside the bounds, then go and check and increment the value. Like, it's just a pain. And writing this sort of thing, no one likes to read it, no one likes to write it. If you have a better way to do that, I would love to hear it, because this is the only way I know how to do this. And yeah, I think I've said it's a pain quite a lot of times by now. But if you take out this bit of code, you know, if we replace it with something like, say, increase surrounding octopuses, then this is actually quite a simple step function, right? And you can kind of almost appreciate it just looking at it like this on one screen. You keep track of which ones have flashed. You increment all of them like the problem said. You should. And then you just keep, and then as long as there are octopuses at above 9, you keep checking the ones that you keep incrementing the ones around the ones that will go off, and you set them all off, and you just keep doing that until you've figured them all out. Once you figure them all out, count how many I've flashed, set all the flash ones to 0, and return. So it's actually quite a simple algorithm. It just made complicated by this chunk of code here. And then once you've done that, it's just a matter of looping. And they actually made the second part quite straightforward this time. They just asked, when does this happen? And it looks like it happens at a relatively low number. And because it happens at a relatively low number, all you have to do is set your loop to a relatively bigger number, but still not too big, and just keep going until you find and the condition that you're looking for, which is in this case, all of them flashing. All of them flashing means that the count is 100, and that's your number. I guess there was a little trick here with the +1, just making sure you didn't mess that up, because the first step is step 1. Most languages, when you do this sort of loop, I will be 0, so you just got to be careful with that. I did run into that problem a few days ago, and that was not fun at all. So yeah, great puzzle, great challenge. I loved it. And yeah, so thanks for joining me today. I hope you enjoyed this puzzle. If you're doing it or if you've done it, hope you had fun doing it as well. And I will see you again tomorrow. Thanks for joining me.